Okay. So, any questions on the previous thing? No, right? No. 25. Examine continuity of f, where f is defined by f of x equal to sin x minus cos x, sin x minus cos x, and that is if x is not equal to 0 and it's minus 1 if x equal to 0. So this is what is the, he said examine the continuity. So we need to look at 0. That means our c value is nothing but c is 0. So LHL would be f of c minus h. So c minus h means it is less than c. So that must be this. So we will take limit h tends to 0 sin minus h minus cos minus h. So this will become sin 0. That becomes cos 0. So you will have the value minus 1. And for direct, f of 0, that's equal to minus 1. That is this minus 1. And RHS should be, RHL limit is limit h tends to 0. So it is greater than, so 0 plus h, c is 0 plus h. So still this will be valid. Therefore sin h minus cos h. So you will have, this will be minus 1. So this and this all are equal. LHL equal to direct equal to RHL. Therefore, no discontinuity. No discontinuity at all. Right? This is 25th. We did 26th to 30th. We have to do 31, 32, yeah, 31, 32, 33, 34. Okay. So 31. Show that the function defined by f of x equal to cos x square is a continuous function. F of x equal to cos x square. So now we'll say let g of x equal to cos x, h of x equal to x square. This is an important thing because we are looking at the composite. So f of x is composite of g of x and h of x. How? F of x can be written as g of h of x. This is what the composite. Okay. So f of x, we need to prove that this is continuous and this is continuous. So let's take g of x is cos x. It is continuous as it is a trigonometric function. Trig function. And we need to look at h of x. H of x equal to x squared is continuous because it is a polynomial function. Polynomial function. Okay. So f of x is continuous. That implies that f of x is continuous since it is a composite function. It is composite of g of x and h of x. That's it. So that's the proof for this. Prove that or show that or whatever. 32. Next question. 32. Show that the function defined by f of x is equal to mod x is a continuous function. Very, very similar. So we go with mod cos x. So we'll say g of x equal to mod x, h of x equal to cos x. Therefore, f of x can be written as g of h of x. So g of x is mod x is continuous function. Why? Because it's a modulus function. Modulus function is continuous everywhere. H of x, the cos x, is continuous, is also continuous. So that implies f of x is continuous because it's a composite. Because it's a composite of g and f, g and h. So that's the proof. All 31, 32, 33, 34, you have to do exactly the same thing. Okay? 33, sine mod x is a continuous function. 33, show that f of x is sine mod x is continuous. So we will say g of x equal to sine x, h of x. You can take any one. Actually, g of x can be mod x. Only the order will change. Okay. So h of x is a mod x. So f of x is nothing but g of h of x, because you are putting mod x instead of x. So now let us look at the g of x equal to sine x. It is a continuous function. Continuous function. H of x is mod x is a continuous function because it's an absolute or a modulus function. Modulus function. Okay. So that implies that f of x, which is the composite of g of h of x, is continuous. Okay. That. So that's why this 31, 32, 33, 34, they can come as only 2 marks questions. It can't come as like a 4 or 5 marks question. So the important ones we covered already. Now the last question of this exercise. Find all the points of discontinuity of x defined by f of x equal to mod x minus mod x plus 1. So f of x equal to mod x minus mod x plus 1. So this also has to be done by the property of the composite functions. Let g of x, it's not composite, it's addition subtraction. G of x equal to mod x, h of x equal to mod x plus 1. Understood, right? This is mod x plus 1. Okay. And you can basically write this as, yeah. So if you have g of x plus 1, g of x plus 1 is mod x plus 1. Okay, so we don't need that. We'll say g of x plus 1. That is nothing but mod x plus 1. Correct? So g of x is continuous. And g of x plus 1 is also continuous because both are absolute functions. Absolute functions. So g of x plus 1 is nothing but h of x. That implies that h of x is continuous function. Therefore, by properties of continuous functions, f of x is continuous since g of x and h of x are continuous. So that's all the English what we need to write for this particular thing. Any questions? No. Now, before we say we completed this, we have to do what is given on page number 163. Go to page number 163.
Theorem 3.
Yeah, 163. There are two theorems are there. Theorem 3 and then not 2, only 1. Theorem 3 and corollary 1. Okay.
Yes.
This one, you actually, rather than me writing, I can write also, but whatever is given in the textbook, it is to be written. Okay. For both corollary as well as theorem 3. Corollary they have given for 1 mark also couple of times. So he talks about if a function f is differentiable at point C. If a function f is differentiable at a point x equal to C, then it is also continuous at that point. Then it is also continuous at that point. First thing, I will tell something for future, what is required for the next exercise or whatever. We did the differentiation already. We know that if we have got f of x and we have found out f dash x, or we call it as a dy by dx. So f of x can generally be a curve. That means you can draw some curve like that. Okay, that's f of x. F dash x, for example, you are trying at a point C, f dash C. Say this is a point C. For example, this is a point x equal to C. F dash x meaning you are finding the tangent at that point. The meaning of this is the tangent. So dy by dx or f dash x is slope of a tangent at that point. In this case, at this point C, x equal to C. Why I am telling this? See, if there is a break, for example, if there is a break at x equal to C, you can't even draw a tangent because we don't know which point it is. So because you are able to draw a tangent, that means there is no break at x equal to C. We are able to find dy by dx. That means we can draw tangents. If we can draw a tangent, that means you can't walk on when the broken point of a bridge, right? We are able to walk at a point, meaning the bridge is joined there, it is not broken. Okay, so that is what this theorem actually means. Yeah. So now we look at the proof as is whatever is given in the textbook. So if he said f is differentiable, let's see. The meaning of differentiation is limit x tends to C, f of x minus f of C divided by x minus C. This is nothing but f dash C. This is a definition of f dash C. So what he is trying to do now, but for x is not equal to C, let's suppose if it is x equal to C, this becomes undefined. Okay, so at x is not equal to C, we can actually multiply with x equal to C. So we are trying to do f dash C multiplied by x minus C equal to limit x tends to C, f of x. I am multiplying both sides with x minus c. That's all I am doing. Okay, into x minus c. Got it, right? So now
Yes, sir.
f of x minus c can be written as this way. So we will talk about the right hand side. Okay, we will talk about the right hand side. So f of x minus f of c can be written as this one, and therefore limit of f of x minus f of x, this one, will automatically become this, get cancelled, and limit f of x minus limit x tends to 0 f of x minus limit x tends to 0 f of c. Okay,
Yes, sir.
so I think if we follow the exact steps, let me knock this out. Okay, I will follow the exact steps so that you don't have confusion. No need to prepare two things. So in here, what he has written is you can write f of x minus f of c equal to f of x minus f of c divided by x minus c into x. Multiply and divide it. Okay, multiplied and divide left hand side, and then apply limits. Apply limits. That means limit x tends to c f of x minus f of c on the left side. Here limit x tends to c. Okay, same thing, f of x minus c, the entire thing. Okay, so the left
Yes, sir.
side, yeah, he opens the bracket, x tends to c f of x minus limit x tends to c f of c equal to, on the right side he distributes the limit. That means he takes the limit for the first one, f of x minus f of c divided by f of x minus c multiplied by limit x tends to c x minus c. He has distributed limit for both the things. So the second part becomes 0. This becomes 0. So that is equal to limit x tends to c f of x minus f of c divided by x minus c into 0. This is equal to this, limit x tends to c f of x minus limit x tends to c f of c.
Okay.
So this entire thing becomes 0 because this is 0. So you got 0 limit x tends to c f of x minus limit x tends to c f of c. So he brings this to the right side. So here there is no x. That's why this becomes f of c. Okay, and here limit x tends to c f of x. So this meaning this is nothing but our direct value. LHL, RHL, whatever it is, this is direct value. Therefore, f of x is continuous. Okay, so the corollary, every differential function is continuous. That means in the top one, theorem 3, we just said at one particular point x equal to c. So what is corollary is, you take anything, any function. He takes an example of f of x equal to mod x. It is a continuous function. So he considered the left hand limit. You will get a -1 value. Right hand limit, you will get a plus h. So
Yes, sir.
both left hand and right hand limits at 0 are not equal. Therefore, f of the differentiation doesn't exist, and hence f is not differentiable at 0. Thus, f is not differentiable function. So here he is saying converse of the above statement is not true. What it means is, I will explain that one. This is a corollary, no need to prove. Every
Yes, sir.
differentiable function is continuous, but not every continuous function is differentiable. So this is only thing not down, but from the graph perspective, he is trying to say that if I draw, this is the mod x graph. So in this mod x graph, at x equal to 0, we can't draw a tangent because you don't have a slope there. Slope doesn't exist. Slope or dy by dx not possible at x equal to 0. Okay. In this context,
Yes, sir.
if you look at the previous answer, like 34th question for the 5.1, we just now did that, right? That I just want to refer back. Okay. Go to 5.1 answers. I'm checking 5.1 34. There is no point of discontinuity. Whereas here, if I apply this particular point x equal to 0, so f of x equal to minus x for x less than 0 is equal to x for x greater than or equal to 0. This is what the definition of this mod x. So when we apply the left hand limit or whatever, so LHL will be 0 minus h, f of 0 minus h, which is nothing but we are substituting minus h is 0, this is the 1, so you will have minus h. So limit h tends to 0 minus h is minus 0. Whereas
Yes, sir.
this one, limit h tends to 0, direct
Yes, sir.
is 0, yeah, RHL will be plus h. So it's a 0. It is supposed to be continuous everywhere. But at this point, that's what he talks about. Okay? He talks about
Yes,
for the modulus function, it is not differentiable at 0, but it is a continuous. It's a continuous function, but you can't differentiate because you don't have a left hand and right hand limits at 0 for the differentiation. Okay, for the differentiation. So just note down whatever is given in the textbook. One line. This is the only one line you need to remember. Okay, that's it. All right. So differentiation part, except for that last chapter, application of derivatives, we have done. Application of derivatives is the one remaining now for us. It is a chapter 6. Okay.
yes,
So any questions on what we are doing so far? Can we continue with the chapter 6, or you want to do physics today? What is your choice? You don't have any choice, anything okay? Then my choice is chapter 6.
Chapter 6.
Chapter 6, okay? Or physics?
Yes,
Physics.
yes, sir. Yes.
Okay. So let's go to physics then. Give me a minute, I'll get the book. We are doing chapter 4 in physics, page 133. 132, 133. So this is chapter 4. Moving charges and magnetism. So here, if you look at the textbook, the main thing is that if there are charges moving, what are the charges? First discussion is charges. We know there are positive charges, negative charges. This is from the charges perspective. We know on the other hand, electrons and protons in an atom. Electrons are negatively charged. Protons are positively charged. And we have looked at, for example, if there is a solid and it's a conductor, the electric current in a conductor can be because of so many electrons moving. So this is movement of free electrons causes the electric current. It causes the electric current. Whereas in solutions,
Okay.
for example, you are trying to do electrolytes, electrochemistry. In that, there will be cations and anions. Those are actually the charges moving inside the liquid, inside that particular solution. So they also constitute the electric current. So here what he's trying is, in any case, whether it's the solutions or the solids, if the charges are moving, there can be magnetic field detected around the charges. Okay, it can be this or it can be this. We will study how the direction is decided. Okay, so that's why he just says remarkable scientific technical progress taken place in 20th century. So electromagnetism is the link between this electricity and the magnetism. So how magnetic field exerts forces on moving charges, okay, or what are the moving charges? I am reading the page 133, just next to that picture, right? He said charged particles like electrons, protons, and current carrying wires. So that is what is the first thing he says. If there is a current flowing, then we can put a galvanometer in that particular circuit and see that there is a deflection in the galvanometer, just like the way we did in the Wheatstone bridge. And if there is a magnetic field, you put a compass in anywhere, in any part of the field around a conductor. If that compass deflects, then there is a magnetic field. That's how we identify the presence of a magnetic field. Now, since he said how these electrons will have a magnetic field created, or if you have a magnetic field already from here to here, and let us suppose the electrons are flowing inside that, whether the electrons will deflect, the wire will be moving left or right. So this is how the field is generated, magnetic field. Here, how the field affects the current carrying conductor. Both the things we'll be talking about in the next few pages. So first thing is, how do we get the magnetic field? So what magnetic force? What is the source of a magnetic force? So this is a non-contact force. Also, this non-contact force we are applying for charges, electric charges, on electric charges. What do we mean non-contact force? In the mechanics, when we want to push this, you apply a force F, and this is mass M, and then this mass will move to here. That's a contact force. A non-contact force is invisible also. You don't see it. Invisible, first thing is invisible. But there is a current carrying conductor and you bring in the magnetic field. Suddenly this conductor may shift a little this side or this side depending on the direction of current. So he talks about the sources. Interaction between two charges can be considered. First is, for example, there is a charge Q, and because of the charge Q, we have electric field E. This is what we learnt already, and we also said you have, for example, here is the entire charge Q. Because of this, all around that, maybe in entire this area, you have electric field E. So if you want to bring in something, then because of this Q, there will be a force existing. So that force is what we said F equal to electric field multiplied by Q, or the electric field equal to F by Q. This is what we learned in the first chapter. So he gives on page 134, E is equal to Q by 4 pi epsilon naught R square into R bar. This is a vector form. In vector form, the electric field E bar equals to Q divided by 4 pi epsilon naught R square unit vector. That's why we put as a R cap unit vector. And then the next one is the force is nothing but Q into E. So now if we talk about the force due to this E bar on any charge Q. Let's suppose you want to bring in this charge Q into this. Will be given by F is equal to this multiplied by that, right? So Q multiplied by E. So we are applying that Q multiplied by E. So this Q is this, and this is the Q divided by 4 pi epsilon naught R square multiplied by R cap. So this is the expression for electric field. This we know, and that's why let's label this as a Fe or F capital E. This is the force due to electric field. So this force is called the magnetic field of several sources is a vector addition of magnetic field. That will come to the point later. So the field at a particular point can be due to one or more charges. You can have one charge, or that's why you put as a capital Q. That means it can be a combination of many charges. If there are more charges, the fields add vectorially. All the things we know it. So just as static charges produce an electric field, the currents or moving charges also produce some field. That field is a magnetic field. Okay, so this field is an electric field, and we write this as F of E function of R. R means function of R. Q divided by 4 pi epsilon naught R square, because this is this R cap. So this is what is called a static force. So the force exerted by moving charges is called magnetic fields, magnetic force, and is represented with the letter B. This is also a function of R. That means if you have the charges flowing this way, for example, they are all flowing this way. From this may be distance R. This may be distance R1. This may be distance R2. So as you go away from the conductor, the field may be weak and weak. The force may be weak. That's why this is dependent on R. And this force is called a magnetic force, and it is also a vector. like the electric force. So it is also a vector field. It has several basic properties, very similar to the electric field. So electric field also undergoes superposition principle, and even the magnetic field also. The magnetic field of several sources is a vector addition of magnetic field of each individual source. So this is the source. In this case, this is the source of the magnetic field. If you have many sources, so superposition principle as applied to magnetic field. So the net magnetic field at a point is the vector sum of fields due to all forces. Forces here is magnetic forces, or rather magnetic forces, all forces by all sources. That means you add up all the sources, which means, for example, you have B1R, B2R, B3R, whatever. So we are now considering at one point. So B1R is going this way, B2R is going this way, for example, and then B3R is this way. So we have to do the vector sum of these three. So what is the vector sum of these forces? If you recall the vectors, let's suppose you want to find out the vector sum of all these, algebraic sum or vector sum we want to find out. So we draw horizontal and vertical axis. Then we'll find out how much is the angle each one is making. Say this is theta 1, this is theta 2, and this is theta 3. So we had made sure that we found out the angles these forces making with the horizontal. Then what we take, we do horizontal component and vertical component of all these forces, of all forces. So this is what actually you learned in 11th standard, but I'll complete it. So horizontal components, H components, B1R cos theta, B2R cos theta, B3R cos theta. So now, how do I find out the total one? B1R is on the left side. This is left, right. This one, B2R is left. B3R is right. So let's suppose we put these things as a positive, this thing as a negative. So the net horizontal component equal to B1R cos theta plus B2 plus B3R cos theta minus B2R cos theta. Similarly, if it is going up, you consider positive for vertical components. So this is B3R sin theta. Let me put here plus B3R sin theta. So onto the vertical, it's a sin theta. B2R also going upward. So plus B2R sin theta. And B1R will be coming down. So B1R negative sin theta. So when you actually do in a calculations, like you will have numbers, right? So you will get one vector for this, one vector for that. Let us suppose net horizontal component is, let's call this as BHR something, BHR. And a vertical component will be B vertical R. So in the vectors we do these calculations, you will know in the math actually when we. So let's suppose both are positive. This is positive, this is positive. So BHR will be this way because it's positive. BVR will be this way because it's positive, like this. Now these two are making 90 degrees. Therefore the resultant will be exactly at 45 degrees, and this is what is actually the B of R. So this is what he meant in the previous thing. If you have three forces acting at one point, then you need to find out the resultant, and that resultant would be, so for example, we have got a particular point. So you have a particular point. At that point, BH can be like this, B can be like this, or it can be like that, any angle. Okay, so that is what the first topic says. Even the magnetic field obeys the superposition principle because different forces combine together, and then you will get a magnetic field. So the next section 4.2.2. So let's suppose there is a point charge Q moving with a velocity v and located at r at a particular time r at a given time t, in presence of both electric field and magnetic field Vr. So he is now talking about, you got a little charge Q. This fellow is a Q charge. And in this particular space, we have both electric field is there in this space. There is an electric field, there is a magnetic field. So this fellow starts moving at a velocity v into this field. So his velocity is v, or you can just say v bar, velocity vector. So now on this, magnetic force also works, electric force also works because both fields are present. So the force on an electric charge, this is a 1 mark question, important question. What is called a Lorentz force? A Lorentz force is the force on an electric charge Q due to both electric field. So that Lorentz force F equal to Q is this Q, and whatever is the electric field you are having, that means EF at that point R, plus Q times of with whatever velocity this fellow is moving. That velocity we said is V, right? This velocity is V. This velocity V, and we will have V of R. This is also vector. This is also vector. So both are vectors. Okay. So you need to remember this formula QVB. QVB. Okay. So this is QER. So that means for magnetic force, this velocity is important. At what velocity? If it is moving slowly, the magnetic field is less effect. Magnetic force is not there. So in a short form, they write it as, this is a F electric, this is a F electric, and this is a F magnetic. Together is called a Lorentz force. So these are the features of this particular Lorentz force. The force is given by Lorentz based on his extensive experiments, and therefore it is named after that person. So the force depends on Q, which is the charge, V, that's velocity, and B, that is a particular magnetic field. The charge of the particle, the velocity, and the magnetic field B. So the force on a negative charge is in opposite direction to that of a positive charge. the magnetic force Q V cross B. It is actually V cross B, but we put it as QVB. V cross B is a cross product. Includes a vector product of velocity and a magnetic field. These things we will be knowing in the next few topics. It is a vector component. Here they will write this as Q into cross product of velocity vector and see, for example, it is moving in this direction and this is a velocity vector, and magnetic force is in this direction. For example, this is the B bar. So these are in the one plane, then cross product will be into the third plane, second plane rather. This is like a 90 degrees with this and this with this. So this is like XYZ axis. X, Y, Z axis. Y is perpendicular to both X and Y, X and Z. X is perpendicular to both Y and Z, like that. Okay. So this you will get later, or if you remember the right hand rule and left hand rule, what we did in the 10th standard, that is this left hand, right hand rules. Okay. So anyway, there is a cross product. So the third aspect is that the magnetic force is zero if the charge is not moving, because the velocity vector, right, zero vector. A moving charge feels the magnetic force. So the expression F is equal to Q V cross B, which is nothing but QVB sine theta into N unit vector. Theta is the angle between V and B. The magnitude of the field, magnetic field B, is 1 SI unit when the force acting on unit charge moving perpendicular to B with a speed of 1 meter per second, that is 1 Newton. So B is considered 1 Newton. So dimensionally, the dimensions of B are nothing but dimensions of F divided by dimensions of Q and dimensions of V. Q is a coulomb, V is a meter per second, therefore Newton second, the units of B. Dimensions or units of B equal to dimensions, we just set dimensions like this, dimensions of F divided by dimensions of Q and V. So F is newtons divided by Q is a coulomb, V is a meters second minus 1. So this Newton second divided by coulomb meter. This is not centimeter, coulomb meter. Okay, these are the dimensions, or this is called 1 Tesla. Okay, magnetic field unit, SI unit is this Tesla. Okay, so that is about the first topic on what is a Lorentz force. Okay. So now he gives an examples of the magnitude. For example, surface of a neutron star. So order of magnitudes of magnetic fields in a variety of physical situations. Neutron star is in the outer space, right? There it is 10 to the power of 8 Tesla. Heavy magnetic field. If you are considering a typical large field, that means in a laboratory we create the magnetic field, we consider that as a 1 Tesla. And near a small bar magnet, which we all played with, the bar magnet, it's 1 by 100 of a 1 Tesla. That is 10 to the power of minus 2. On the Earth's surface, 10 to the power of minus 5. The human nerve fiber, there is very tiny magnetic field, that is 10 to the power of minus 10 Teslas. Interstellar space, it is 10 to the power of minus 12. So in general, he has now talked about the magnetic field. That's all this first topic is. The next one is magnetic force on a current carrying conductor. Magnetic force on a current carrying conductor. This derivation, small one, but still it can be given, okay, because we are now
Okay, sir.
talking about magnetic force on a current carrying conductor. So the current is due to the electrons, okay. So I'll write as a separate topic. So whenever they say magnetic force, it must be due to magnetic field something, okay, on a current carrying conductor. So consider a rod of uniform cross-sectional area A and length L. So we consider now, let's suppose this is a rod, uniform cross-section area, that's equal to A. That is, this is A. Okay, the length is L. This length is L. This is the area A. Okay, so length out. So it will again have the mobile carriers. One kind of mobile carriers, they can be, for example, the charge carriers can be electrons, or the charge carriers can be some positive charges. So we want to find out, we had done already, you also had done the total number of carriers equal to n into the volume. N is carriers per unit volume. That means it can be electrons per unit volume or positive charges per unit volume. Therefore, this is n into volume. That's nothing but n into A into L. These are the total number of carriers. Got it, right? So for a steady current I in this particular rod, we assume that each mobile carrier has an average drift velocity. Let Vd be the drift velocity of mobile carrier. He doesn't say electron per se, okay, mobile carrier. It can be a positive or negative. Therefore, we know that the force, if there is a magnetic field B, so the force on them F is equal to whatever we have done so far. That means we have Q as well as the drift velocity cross product of the magnetic field B. But we know this Q is nothing but this total charges. Therefore, you will have N A L multiplied by Q. If it is only one, I would have put Q. Well, this is the total number. So this multiplied by Vd cross B. This is a cross product. So that's what is given as I into L cross B. So he just takes out this part out, okay, and then because it is along this particular thing, the current is going along the length, right? The current goes along length L. That's why he considered this as NAQ, okay, NAQ VD. In fact, you can put the VD also, QVD, and then the cross product of L and B. Okay, so all this part, whatever you have done, so this entire thing, we can write it as current density multiplied by A. J, this is the current density multiplied by A. This is A is there. This is the remaining current density. Okay, so L cross B. So current density multiplied by the area, you will get current. That's why you will have I L cross B. So this is the magnetic force. So this is a brother-in-law. You are wondering what is this, right? This is to be remembered as FB is equal to BIL, BIL, if you are taking magnitude.
Yes, sir.
This is B, this is I, this is L. Okay. Otherwise, it is like I into mod L mod B sin theta and n cap. That's a full part. All right. So this is for one particular conductor. Okay. So we can calculate the Lorentz force on by considering it collection of linear so many strips and summing it up of the last line in this. The total force would be, because we consider this as a small length L, because this part we considered is a small part of the conductor. In this one, right? Yeah, this is only a part of the conductor. If you take a total conductor, then you have to sum up all the forces. That's what he is telling in that. Okay. Then we'll come back to the numericals later. Whatever is the relevant numericals, we can do that. Motion in a magnetic field. So now we are considering whatever velocity the charges are moving. So this derivation also is important. Okay. So the motion of the charges, the motion of a charge moving in a particular magnetic field. What we did just now is motion of the charges as in the form of a conductor. That means current carrying conductor as one thing, we put it in a magnetic field. The second one, what is 4.3, is motion of the particular charges in a magnetic field, individual charges. Okay. Obviously, the conductor contains charges, mobile carriers. Now we are going ahead and looking at what is the effect on each particular charge and how that particular thing is going in a like in a circular motion, how this is impacted. That is part of the next topic. Okay. So let's. We do have another some more 15 minutes time. We can continue this nicely. So you are understanding, right? There are no issues with the your okay. So wherever is a derivation, I will bring it up. We again go through the derivations one more time when we do the revision. Okay. So here he combines a charge as a particle, and so he considers the mechanical force. That means this is running at some velocity v. Therefore, it can be having some kinetic energy, or it may be moving in a particular centripetal force will be there if it is moving in a circular fashion and all the stuff. So what he is trying to say is that there won't be any work done and there is no change in the magnetic field, magnitude of the velocity, if something is moving in a circular fashion. So in the case of a motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle. So look at the picture 4.5, figure 4.5. So he has put cross mark, cross the into means magnetic field is going into the page. That means it is coming in from our face and then entering the book or the page, and it is the tail. The cross indicates the tail, the into indicates the tail of the magnetic field. So if the magnetic field is going into the page, and for example a plus q is moving in a circular fashion on the page, that means he has given the tangential velocity v. This v and b are perpendicular. That's what he is talking about. So the magnetic force is perpendicular to the velocity of the particle. Since it is perpendicular, no work is done and no change in the magnitude of the velocity is produced, even though the charge is changing its direction. There is a momentum, okay, because it is the velocity direction is changing. Okay? So unlike the force due to electric field QE, which can have a component parallel or anti-parallel to motion and then transfer energy in addition to the momentum. Therefore, we are considering motion of a charged particle, uniform magnetic field. Consider the case of V perpendicular to B, the perpendicular force QV cross B acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. That is the reason he has drawn the circle. So the particle will describe the circle if V and B are perpendicular to each other. That's the one which we need to be highlighting here. So if it is not, if the V and B direction are not perpendicular to each other, then you may not have a perfect circular motion. It could be elliptical. Okay. So that's why next point he says, you look at the graph in 4.6. So y-axis, x-axis, and z-axis. Along x-axis, you got the magnetic field P. So that is where the magnetic field direction. And Q is trying to move along y, the direction y. That's what he says. If the velocity is perpendicular to B, then it automatically makes a circular motion and tries to go almost in the same direction, exactly in the same direction as B. But then, like a cylindrical fashion, it will be going. So if the velocity is a component along B, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B is as before a circular one, thereby producing a helical. Helical means like a spring. Okay. So if that particular charge is going in a circles, obviously the centripetal force acting on that would be mv square divided by r. This is straight away from mechanics. Okay. So this acts perpendicular to the path towards the center of the circle, and it is called the centripetal force. So what he is trying to do, the only force that gets experienced by this charge is the centripetal force. And therefore, he writes that mv square by r equal to qvb. Therefore, how much is the radius of this spring is r equal to mv divided by qb. These are all at 1 mark questions. The formula what you have seen that right, 4.5. The radius of the path taken by the charge in the magnetic field given by the mass of the particle multiplied by what velocity it is moving with divided by q into b. Okay. But we know that v, the velocity v, and the angular velocity omega are related as v is equal to r omega. And therefore, we are now replacing that mv with the r omega. So that gives you w is equal to v by r or w is equal to qb by m. This is also the formula to be remembered. I will write these things in case you are getting lost. So we have drawn that kind of helical part. This is that plus q going, and this is this magnetic field, and this is the x direction, this is the y direction, and the particle will be moving this way, and this is the drift velocity, and this is the z. And so what it says is mv squared by r, that is the centripetal force, is equal to qvb. And from here you will get r is equal to, so r is equal to this 1v gets cancelled here. Okay. So mv divided by qb. Okay. In other words, that implies v is equal to qb into r divided by m. So the angular velocity is omega. So v is equal to r omega. Therefore, omega is equal to v by r. So qb r by m, 1 by r. So r gets cancelled. So angular velocity is equal to qb by m. But if it is running at a frequency, suppose we know it's moving, then we can have a frequency for this particular charge. That either we can call it f or you can call it nu. Let me call it as f. Okay. So when I take
Yes, sir.
f, then w is equal to 2 pi f. Omega is given as 2 pi f. So you can consider now 2 pi f is equal to qb by m. So the frequency f is equal to qb divided by m or 2 pi m. So this is the frequency with which, the frequency meaning, so when something is going like that, right? So if you draw from here to here, it will travel some distance. So it is coming to almost the same position after going like this, and this is called one cycle. So how many cycles in 1 second? F is nothing but number of cycles in 1 second. So that is given by this formula. If you know the magnetic field and if you know the charge, you know its mass, then this is what is its frequency. Okay. This is required to
Yes, sir.
calculate actually the particle accelerators. So the last point he gives in this is the distance moved along the magnetic field in one rotation is called the pitch. Pitch is nothing but its drift velocity multiplied by the time taken. Okay, so
Yes,
so so VB is whatever is the velocity with which it is moving, denoted by V. Velocity parallel to the component of the velocity is VB. If it is moving with VB, as I said, the pitch is nothing but I was actually explaining that. So the pitch is also one mark question. Pitch equals to whatever is the velocity B into T. So this VB, T is nothing but 1 by F. So VB into 1 by F. Okay, let's not put into. We will just make it as 1 by F only. Get this QB by 2 pi M. QB by 2 pi M. QB divided by 2 pi M. So that's equal to 2 pi M VB divided by QB. So this is what the pitch formula. So the radius of the circular
sir.
component of the motion is called the radius of the helix. Okay. So much we can do today. We can probably stop because next one's also theory, not derivation yet. The derivation will come in 4.5. The next class, I think the Wednesday class, we can cover these derivations. Okay, important.
Yes, sir.
Biot-Savart's law. Okay, Ampere's circular law. All these things, solenoid, all the things we can cover in the next class. All right. So, any major questions you have? Let's go back and then do a revision, quick revision. Okay.